formal proofs into libraries, we may need to kind of change our processes and change things like that. So I'll hopefully discuss a bit of that as well. So what does it mean for an AI system to prove a theorem? Well, I guess it depends who you are, where you draw the line on what is AI and what is not. But certainly back in the day, people would have called any sort of symbolically executing algorithm AI, right? So maybe you wouldn't call this AI, but this is an example of a lean proof that uses the n-lin arith tactic. The n-lin arith tactic runs a simple bespoke algorithm, right? It runs Fourier multiplication elimination. You could think of it as running, Gaussian elimination or something like that instead if you prefer. But what it does is it solves a very well-defined problem, which is any sort of goal, which is a sort of a linear combination of the hypotheses. Think of it as something like that. So these are some really complicated examples, but this is sort of like the first kind of rung of like computers proving theorems. And I've chosen this example because it's actually quite complicated. Like, I don't know if you can read this problem, but it's a relatively complicated statement. It's not a linear problem at all. It's sort of highly nonlinear. I wouldn't necessarily know how to prove it, and yet we're kind of using this off-the-shelf automation with a lot of different arguments to kind of prove something quite non-trivial. So even though this is bespoke, it's kind of handwritten, it will only apply in the domain that it was designed for, and it will never apply more generally. It's still extremely useful. It's still quite powerful. Kind of one step above this, there are tools that are kind of higher level, let's say, automation. So in Lean now, there's kind of a tactical grind. And for those familiar, this is sort of inspired by SMT, satisfiability modular theories techniques. So here we can see kind of a relatively non-trivial goal from program verification, which would be that this insertion sort algorithm is correct, right? That's something that you might care about. You've given a sorting algorithm, you want to know it's correct. And what's kind of interesting about this example, which by the way is from the website at the bottom, is that the proof is basically using this one tactic grind 3 times, okay? So this is insertion sort proved correct. They're an SMT-like tactic, and it's extremely concise, which, of course, hopefully means, though maybe not, that it's easy to produce. So why do I say maybe not? It's because one had to tag certain definitions and lemmas as grind definitions and lemmas. So this is a bespoke algorithm still, but it's user extensible, okay? So it's still running a kind of a fixed procedure to prove the theorem, but the user can kind of expand the domain beyond what it was originally designed for. So still it's kind of fundamentally a sort of symbolically executing kind of bespoke algorithm. So that was sort of how automation in proof-assistant Lean at least looked until somewhat recently. What's changed recently is the advent of AI systems, right? So these are sort of no longer purely symbolic. They're sort of probabilistic systems generally that suggest steps and proofs, and they're guided by sort of learned heuristics. In fact, it's extremely hard generally to kind of say exactly what is learned and exactly how, but they are trained to produce proofs either from kind of examples or, as we'll talk about, via reinforcement learning, which, yeah, I guess you could say that's being learning on examples, but the point is the examples are no longer simply human-written examples. There are self-generated examples. So these are able to solve now quite challenging problems and operate kind of autonomously for much longer periods of time. And I guess the key difference there is really because they only, because they're not kind of executing an algorithm which has kind of a fixed domain, they at least probabilistically have a chance of solving hard problems. So if you kind of run them long enough, they will, generally speaking, solve harder and harder problems. So of course, we do see a kind of a plateauing, right? As with most things after a kind of some period of time. So they're really more flexible than kind of bespoke automation. And they can often really surprise you. And that's what makes them quite interesting, right? We can train them and we can't say exactly what they'll learn and when, but they certainly do seem to learn to be significantly more powerful at this point than kind of bespoke automation is. So the other kind of really magical thing about these systems is often they're based on language models, right? Producing proofs in a proof system like Lean is a language, a formal language. But often these language models are pre-trained on natural language. And what that means is that these systems are often able to kind of interpolate, when trained correctly, between natural language and formal language, which is, of course, kind of, at least for me, one of the dreams, right? To kind of have the benefit of a formal system without losing, talking to a co-author in a well, English or whatever other natural language you prove, and kind of expressing yourself in a slightly imprecise way, but letting the formal system kind of fill in the gaps. So personally, I find this one of the most exciting things about these systems is the kind of ability to interpolate between natural and formal languages. So these will definitely use the things from the previous page as building blocks, right? These are not sort of replacements. And in fact, it may not surprise you to know that these examples on the first slide were, of course, written by an AI, namely Aristotle, which is the AI we've been developing. And you could probably sense that from some of the slight oddities here about, spacing around brackets and putting semicolons everywhere, but probably more likely from the fact that these calls to Emlyn Arith are quite long and quite detailed, right? And probably longer than you might see a human write. And, just to give a bit of a detail about, kind of what's going on here is a common way to prove positivity of some expression is to express it as a sum of squares, right? This is kind of a well-known technique for proving positivity. And what Aristotle has basically learned to do here is to prove quite complicated inequalities via finding the sum of squares certificate, right? So basically, you can think of this kind of expression at the bottom as a complicated sum of squares certificate for the problem at hand. Once again, I don't expect anyone to pass this problem immediately. It also, by the way, is actually a proof of the negation of this original statement rather than the original statement itself. So it's a little complex, but that's just to give you a kind of a flavor of this thing. So yeah, what is Aristotle? It's a large language model-based system for theorem proving in lean, and it's trained by reinforcement learning on lean feedback. It's capable of at this point, writing entire projects pretty much autonomously or with minimal direction at least. And anyone can access it at aristotle.harmonic.fun. You should go there and you should get an API key and download our beautiful textual interface that, of course, we hope to replace with something better as soon as possible. But for now, you get this beautiful text interface and you get a few options. You get an option which is to fill in all the gaps or the goals, the sorries that were left in your lean file. You get the option to provide, I don't know, your paper or your course notes or any other mathematical content that's in a text file or a markdown file or a text file and have it be autoformalized. Or you get the option just to give some generic instruction, which is, a bit more free form, and it allows you to give relatively minimal direction, right? You could say okay, prove the isoparametric inequality for me, right? And you could let it decide exactly how it's going to do that and, what structure the thing will take. And, it's sort of trading off effort on your end for maybe slightly more variable results compared to option number 2. So yeah, I encourage people to try it out and, see what interesting things you can do, and obviously report any issues you find to us, because we want this thing to be as good as we possibly can. So what have people been doing with it? What can systems like this do now? I'm going to give a bunch of examples of some of the interesting things people have been doing with it. So one area that has generated a lot of recent excitement is this database of Erdős problems. So Thomas Bloom has collected this database of problems, and his method is basically to look, so first of all, for those who don't know, Paul Erdős was an extremely prolific combinatorialist, additive number theorist maybe, who traveled around the world writing papers with people, and he wrote, I don't know, I forget the number, hundreds, if not thousands of papers in the course of his life. And what Thomas Bloom does is he looks at the papers and he finds all the question marks, and most of those become sort of open problems, right? So these are problems that Erdős stated, some of which have received a lot of attention, some of which have maybe not been thought about so much, some of which may be sort of trivially false, some may be trivially true, some may be, among the hardest problems in mathematics. And there is now a sort of database of 1,000 of them, right? And so the fun thing when you have a sort of an automated system and you have a database of 1,000 problems is you can sort of try the automated system on all of 1,000 problems. So people have been doing this, right? They've been taking Aristotle and feeding in these Erdős problems and finding sort of trivial counterexamples, finding errors in the formalizations, but in some cases finding really interesting proofs. So these have varied from sort of like pure AI solutions to AI-assisted solutions. People are using a combination of these big FLMs like ChatGPT and Aristotle and kind of various other kind of techniques. They're feeding in ideas. They're coming up with kind of complicated pipelines. But yeah, the interesting thing is that there have by now been kind of at least purely kind of new solutions to some of these problems using Aristotle and using these other systems. So for example, this is problem 124, which was sort of a little bit unclearly stated, let's say. So we'll say maybe this is a version of problem 124 that Boris Alexeyev fed to Aristotle. And I think he writes in his blog post here at the bottom that he was not emotionally prepared for Aristotle to come back with a proof. So Aristotle certainly came up with a proof for this version of the problem that, as far as we can tell, is new. I'll get back to that point in a moment. And various other people, including Kevin Barreto here in Cambridge, I don't know, I never met you, so if you're in this room, hello. If you're not, hello. Have kind of really tried a number of these problems now, and there is basically a kind of ongoing project to sort of catch them all in a sense, and try AI on all of these problems, and collate the successes and failures, and kind of work out which problems are interesting for human study and which ones we can get new ideas from AI, and kind of start kind of classifying these problems more rigorously. So Boris Alexeyev, once again, has kind of scaled up his pipeline, and he produced this kind of repository by now, which has over 90,000 lines of lean code with solutions to Erdos problems. So some of these are autoformalizations of existing solutions, some are new solutions, some are variations. But I think what's very interesting here is that I claim it would have been basically impossible for him to have produced these 90,000 lines by hand, right? Like this is clearly kind of accelerated, his workflow here for doing this. And I've spoken to Boris. I think, in some sense, he really is quite worried about correctness, right? Like he really wants to know that all these proofs are correct. And this is his way of, convincing himself and of course others that all these proofs are valid, right? And that, we're not building on an unsolid foundation. So yeah, vast majority of these formalizations were kind of collaborations, let's say, with Aristotle. And yeah, you can see the list there. I encourage people to check out these links. They're quite interesting. They're kind of stories about the process of solving some of these problems, and a kind of a list of which problems have been tried by AI, which ones have been solved, which ones haven't. And yeah, it's kind of growing day by day, and it's kind of fun to look at. So that's the Erdos problems. What else have people been doing? Well, they've been autoformalizing their papers. So this is Bartosz Nastrecki, who's had a kind of a group theory puzzle that I think came from a kind of a game. And I think he gave it to one of the GPT models. They suggested a proof, and then he sort of like autoformalized the entire thing. The point here is that this is like 2,600 lines, right? This is an extremely long file. I would claim that this is, you could just, if skeptics among you might say, maybe it's just really long because Aristotle put a bunch of like unnecessary new lines in the middle. I would claim this generally needs to be somewhat long, right? This is not an extremely inefficient proof. This is just quite a complicated theorem to express. And this has been sort of one of the issues with formalization for a long time, is that the ratio of informal to formal is generally speaking kind of too large, right? We generally speaking have difficulty formalizing things because the amount we need to write is really too much for humans to be able to do it on the same timescale as they do with informal solutions. So this, I think, is a very positive sign that we can now start checking our papers in real time in at least some areas. Just 2 days ago, Boon Swan Ho, who I think is actually an undergraduate in National University of Singapore, wrote a paper called A Generalization of Hunter's Entropy Inequality and added it to arXiv, and he autoformalized it, right? I think this was a little bit shorter, and the paper itself is only sort of 4 pages, but I think what's clear is that this is now possible to do kind of real-time formalization for at least short and self-contained papers, right? And so the challenge ahead is to scale to longer papers and papers that depend on mathematics that this is clearly an inequality about one-dimensional, I guess, real numbers. So relatively few dependencies, and so some areas of mathematics will of course require much more, and that I think is the next stepping stone. in terms of a more traditional lean project, Terence Tao's explicit analytic number theory network project has been recently started. And what's interesting here is that we haven't just been proving things. Aristotle has also been sort of finding incorrect statements in at least a couple of different ways. So the first way is just directly finding counterexamples, right? So in this case, the counterexample is a large number. It's not a kind of a trivial counterexample. 2,010,880. So this is the sort of thing that a human probably would have discovered eventually, but likely has been accelerated by using AI. The other interesting way that the project has been vetted, so to speak, is when a proof is found by an AI and you study the proof and you realize that the proof was too easy for the statement that you wanted, you kind of realize that something must be wrong. So in this case, there was a definition that was made that was too weak. And this was discovered by noting that Aristotle had found a proof that used Bertrand's postulate. So Bertrand's postulate is one of the first kind of like estimates you can give about the density of primes. And so getting a non-trivial result out of Bertrand's postulate, shouldn't be possible, right? That's sort of a vibe that number theorists or analytic number theorists would have. And so in this case, it was noticed that there was a mistake in the definition because the proof was too easy, so to speak. So that's another way you can kind of vet your projects with AI. And of course, it's completed entire sub-projects, right? So there's a couple there. And it's sort of filled out parts of the project that humans might not have bothered to do. So deriving older versions of theorems as consequences of stronger ones is a good thing to do to check that you've stated them correctly. But probably a human wouldn't have bothered to do that themselves. So people are using it, Aristotle and other tools to fill out libraries like MATLib, lean quantum information theorem, to resolve the status of kind of unclear informal work in the latter. And we applied the model to Dish's IMO and got 5 out of 6 problems, which would have been kind of like a gold medal score if we were a teenage human. Unfortunately, we're not. Clearly this is by now quite capable. People have used it to solve the problems from this year's Putnam exam, right? And I would say all of these, apart from the IMO results, are from regular users making requests to the website. So this is not necessarily the case anymore that sort of this is limited to people working in an AI company, who have sort of full access to these models. It's really just the case that you can just ask these things and get the results out, publicly accessible version. So I'm very excited about that. One of the most interesting things here, I think, is that it's a mixture of people who are lean experts, who are math experts, who don't know lean, and basically all the parts of the Venn diagram, right? So you have people who are really experts in neither, who are still kind of having fun, checking their putative mathematics with Aristotle. So that's, I think, very interesting. So yeah, please try it out and throw in all your favorite theorems and conjectures and see what happens. So those examples were all about mathematics. So I wanted to give one about program verification that I think is really quite cool. So there's a system called Velvet, which is developed by the 5 people named there as part of Ilya Sergey's lab in NUS again. And they published this in Popple, I guess, a week or so ago. And this is a Daphne-style verifier for imperative programs embedded in Lean. I'll show you what that looks like in a second. And it combines some automation with interactive Lean proofs, and it supports, all these kind of things you might have in imperative programs, right? Mutable state, loops, non-determinism, etc. And so what they did is set up a type of memory allocator, which is called a first fit free list memory allocator, and basically proved the entire thing correct, essentially purely with Aristotle. The point here is that, these systems can do program verification as well as math, right? I think we, certainly thought about math a lot more at the beginning, but by now they're perfectly capable of doing sort of a much wider distribution of tasks than maybe originally were trained for. So this is the example here, I'll just show it. So this is an example of a type of memory allocator, which has memory blocks, which are in a linked list. And the way it allocates is it traverses the linked list step by step until it finds a memory block that is big enough. At such a point, it allocates that block and removes it from the list and moves on to the next one. So this is, I'm not an expert on memory allocators, I will say. So, take this with a pinch of salt. But this is certainly something that, has a sort of a non-trivial specification in this case. So you can see the specification is written here. And what's interesting is they fed this to Aristotle, and Aristotle gave them, first of all, a bunch of lemmas, right? Certainly, if you imagine a linked list, one of the key kind of concepts to deal with there is sort of paths in this list and to give all the kind of obvious things about paths. So Aristotle first gave all these kind of obvious statements about paths, so to speak, and then started proving all of the properties they fed to it. So that's 1, that's 6, right? Some fairly long proofs. And eventually, after Aristotle proved all of these parts of the specification, they could just use their kind of custom tactic. I don't understand how all this works, to be clear, to basically prove that this memory allocator is correct. So I think this is quite cool. I think this is probably the most compelling example I've seen so far of interesting program verification being done with Aristotle, and I hope there will be much more in the future. So yeah, what changed that made all these things possible? I think the key thing is moving from bespoke tools to a kind of a learned search. And so when you do that, you just allow yourself a lot less human kind of effort involved to design these systems and to think of every possible use case and every possible kind of variant, right? So basically what I'm saying here is that, machine learning in the sense of how it's used today to mean models sort of trained either via supervised fine-tuning or kind of reinforcement learning, rather than kind of explicit algorithms, has kind of enabled this massive jump in kind of capability, right? So in the case of harmonic, at least, right, we have a sort of a proof search policy that is learned and updates itself from experience rather than being hand specified. So let me now go into a bit more detail here. So the main driver of recent progress is really reinforcement learning. People tried machine learning for formalization for a while, and there was some success, but reinforcement learning is really the thing that has accelerated this. So instead of just training on human written examples, of which there are some on the internet for formal languages, but not so many, we reward a model for getting a correct proof, and we train the model sort of iteratively just to maximize that reward, right? So whenever it does a good step, we kind of upweight the parts of the model that led to that good outcome, and you could do the opposite, for example, as well. So in mathematics, you could do this reward in many different ways. You could do it kind of informal reasoning, and you could reward it for reaching a correct numerical answer, right? You could reward it for writing code that compiles and produces the correct answer. That would also work. You could reward it for producing a proof that convinces another kind of fixed model, right? This is also something. And the last one is the one that harmonic is doing, which is producing a lean proof that kind of solves the goal, right? So there are kind of pros and cons of each of these that maybe I won't go into now, but I gave a talk over the road, no, right there in that building, in the Isaac Newton Institute in like July. So yes, feel free to check that out if you want more detail on kind of the fig proof. Yeah. Yes, June. Okay, yeah. Thank you. So yeah, this kind of turns theorem proving it into a kind of like a game, right? The model learns to play better and better from just kind of self-play against this kind of game. So how did the kind of the IMO system look? So this is a white paper we published after the IMO about the system we use there. And of course, we're constantly improving and tweaking things. So yeah, some of the details will be a bit different in the system that is running today, but I hope this gives you kind of some idea of kind of roughly how it works, and at least satisfies some curiosity about how to build such a thing. So first of all, it kind of bridges between natural language and formal lean statements. And it kind of uses a large model to kind of propose both informal proof sets and propose tactics, right? So it's sort of not purely formal and not purely informal. It's kind of sitting somewhere in the middle. And so from interacting with lean, it gets precise feedback about the results of tactics. And that allows us to train it. In the IMO system, there were sort of two main subsystems, right? There was a system that exclusively searched for lean proofs, right? Which I'll talk about in a second, but it's kind of a Monte Carlo graph search over lean tactics. And there was a system for kind of proposing lemmas and kind of iterating on a set of lemmas to kind of work out a correct high-level strategy. So, a lemma, it might suggest, might be proved by the kind of graph search system, or it might be disproved. And kind of based on the set of proved lemmas, maybe new lemmas would be suggested, new proof directions would be kind of tried. And I'll give a kind of a schematic diagram in a second, but hopefully you can kind of imagine how that would be more likely to lead to a kind of a good high-level strategy. So, what do I mean by a Monte Carlo graph search? Well, if you imagine a lean proof, and you imagine kind of writing it iteratively, generally you might do something like this. You might kind of write the next step that you know how to do, and you might kind of stub out parts you don't know with the keyword sorry, which means, this is kind of a hole that I'll come back to and fill in later. And so the location of a sorry basically corresponds to a sub-goal a sub-goal of the proof in a sense. And so if you imagine these as a kind of graph where, new tactics possibly with stories in are edges, you get this kind of graph-like structure between states and, kind of tactics being the actions between the states. Technically, this is a hypergraph in the kind of setup we have, because you could have a tactic with two stories in, which would produce two goals. So technically here your action is kind of has a target of two different states. That complicates some things, but think of it as a graph, I would say, for now. So this is roughly kind of how it would look, and this is really what Aristotle is doing. It's proposing these tactics until we get to a point where there are no goals left, and then we know we've completed the proof. Okay, so yeah, this is basically what I just said. Yeah, we have states, we have actions, and one kind of small detail is that, we can also negate things in our setup. And so we have this kind of and or not tree, basically, where, if you are in a state where you propose multiple different tactics that might work, then you only need one of them to work. But if you have an action where you have multiple states remaining, then you need all of them to work. And if you disprove something, then you can, of course, propagate that around the tree. So we merge sort of semantically equivalent states, right? So states that really, maybe look marginally different, but represent the same goal, we kind of merge them. And we have a big transformer that serves as both the policy and the value function. So it's a highly parallel Monte Carlo graph search that sort of focuses effort on the hardest remaining subgoals. We're going to help prove the theorem. So I mentioned this kind of informal lemma generation kind of outer loop. And so this takes a target theorem, and it sort of generates sort of informal proofs and splits them up into lemmas and attempts to formalize the lemmas, right, using the graph search. As it does so, it can kind of iteratively kind of refine the informal proof, but based on kind of which lemmas succeeded and which ones didn't. Sorry. So this is a way of kind of taking this graph search algorithm and kind of leveling it up to work on kind of much harder problems than it might do on its own. So this is kind of bridging the gap between a kind of a purely informal system and a purely formal system that we found kind of very effective. So there are other systems that have been trained to do this sort of thing that have worked sort of purely formally. And while that's definitely like an interesting approach, I think we believe in the kind of the mix of informal and formal as a profitable strategy. So yeah, a bit more on that. We kind of, as you saw in the examples, we have a model that kind of suggests both kind of comments describing the informal thought and the actual kind of formal lean tactic, right? So this is a kind of, once again, another way in which we're kind of mixing formal and informal, even at the low level. And we find that kind of helps, have the model learn from both informal proofs it's seen and formal proofs it's seen, as it can kind of associate the two better, right? Presumably internally, the sort of representations are shared. And so we train all of this stuff via reinforcement learning, right? We take problems, we attempt them, when we succeed, we upweight kind of, yeah, what led to doing those actions, if that makes sense. And we kind of iteratively improve in that way. And all we really need is a big source of problems to try out. Okay, I'm going to skip that. So, and I'll skip that because I already kind of mentioned it. So I think people should maybe rethink their workflows a little bit. So I'm going to move into maybe a bit more kind of high-level picture. So previously, when people work in theorem prover, they kind of walk through a file kind of level by level. Like maybe they have a big goal they want to prove and they kind of work backwards. Maybe they have some notes or maybe a blueprint in the lean case or a paper or something. And they kind of, work kind of naturally. They kind of prove some lemmas. They realize some things are missing and they kind of, push in one direction. Maybe they add a hypothesis here and there. And, I think when you work like that, it's actually a little bit harder to use these tools effectively. So, when humans kind of thinking and kind of typing with the main bottleneck for producing formal proofs, they kind of make sense. What I would suggest people try is kind of like, think of this as an AI coworker, right? So spend a little bit of time designing the kind of the high level structure, the main theorems you want to prove, what the useful lemmas might be, maybe just purely informally, and kind of submit it to one of these AIs, right? And then move on to another project, right? And kind of run a bunch of these in parallel, right? And I think if people kind of adopt this workflow, they'll have a bit more success than kind of, reaching a single point where you get stuck, submitting that to an AI, sort of waiting for it to come back, and then resuming, right? So I speak to many people who kind of instinctively do that and find that they're not really getting much utility out of it because they're sort of just waiting for the thing to do something. And in the meantime, they can never help themselves and they start proving it themselves by hand. So I would really think of this as like giving work to kind of, I don't know, coworkers or like, really talented students that you have and just kind of directing them at a very high level and kind of seeing what sticks, right? So think of yourself as managing like a team of sort of hardworking and junior collaborators, right? So they're not going to do everything you ask, but they're willing to give anything a go. And, they're sort of infinitely parallel, right? So it's a different way of working, I think. And, maybe it's a bit, unfamiliar at first, but I think it can be quite fun once you get the hang. So, yeah, the other thing to say is these collaborators are only going to get better. So I would say learning how to use them effectively is sort of like a long-term investment, right? And so, yeah, I think we should kind of think as well a bit about like what becomes worth working on. I think as someone who's done formalization for a long time, I think it's very easy to kind of dismiss some of these big projects, right, as being just like too out of reach, right? And I think if we really start using these tools effectively, we can do like significantly larger projects, or maybe, well, there have already been very large projects, so maybe I shouldn't say that, but we can do projects that used to take a team of humans a year, maybe one human can do it in a few months, right? And I think we should be really ambitious with the sort of things that we try and formalize now. And I would encourage people to like, try much larger projects than they did before and kind of integrate these tools and, just fill in the gaps where needed, correct the direction when needed, but not to do everything kind of by hand. So I would say we should be ambitious about what libraries like Mathlib should contain. And that's my schematic. View of that. Who knows if this will happen, but I hope it does. Because I think like, it's very easy if you work on formalization to kind of get maybe a little bit used to the state of play where, we're so far away from research mathematics still after like, 653 contributors over many years in Mathlib's case, and many, many, many more in other languages that have had longer histories. And, I think if we really want to actually make these tools kind of useful for research mathematics and things like that, we need the graph to change slope. So where are the limitations? I think right now, the limitation is producing kind of like high quality maintainable code, right? And I don't think this is a necessary limitation of these tools, but this is just kind of like a second order kind of concern to proving these, right? So, a lot of the effort in developing these systems has gone into, can they produce proofs at all? And I think producing kind of clean and maintainable proofs and proofs that people like enjoy looking at or proofs that are in good style, so to speak, that is more of a, I guess you could say, I mean, it does have some technical elements, but it's sort of an aesthetic quality, right? And I think that's the thing that's going to come next, right? So things that are sort of aesthetic qualities are a little bit harder from sort of, a reinforcement learning perspective, because they need to be measured, right, in order to be rewarded. And some things like maintainability, there are many stories amongst formalization kind of communities of people, writing things one way and realizing 6 months later that they should have done a different mistake, right? So this is a kind of a reward signal that takes place over a very long period of time, right? If you only realize 6 months later that you made a mistake, well, you have to kind of run something for 6 months, right, to kind of realize that, right? And so this is kind of like I guess you could say it's sort of the time horizon of the task is much longer to get this sort of signal. And so this is kind of why, this is one interpretation at least for why, this is kind of the next challenge, so to speak. So, I think that, many people in this room are really interested in, and I certainly also used to do a lot of before I started doing a bit more machine learning stuff, were kind of like automated quality control, right? I think if we invest a bit of time in automated quality control, we can really start deploying these systems like willy-nilly, right? Like if you can sort of guarantee that the quality you get out will be sufficiently high, then we can really start deploying these things much more widely, right, than we do right now. So I think that's sort of the next, the next challenge here. And I hope that we'll kind of solve it all together. So I think another kind of aspect here that I think is very interesting is this sort of question of like informal and formal LLMs. And I would like to kind of convince you at least why formalization is going to be important, right? So I think we've seen that there are many kind of purely informal systems, right? Things like GPT 5.2 that are now very capable of producing, very long and complicated informal proofs when prompted with something like a knowledge problem. And, these systems are reasonably reliable, but I think as they get better and faster and start producing more and more stuff, I think we're going to get a little bit tired of checking their correctness. So my kind of claim is that even if we are using purely informal systems, we will want formalization on top to know whether something is kind of worth our time to look at, right? So this is already kind of a paradigm we're seeing sort of play out with these other problems is people are, asking something like GPT for a proof, and then they're feeding it to Aristotle so that they can know whether or not it's correct and know whether to invest their time in reading it, right? So if you're asking a model for a proof of 1,000 problems and it comes back with 100 proofs, you don't want to be reading them by hand, right? Like we do need formalization on top of the informal models as a way to ensure that they are, correct and therefore, containing good ideas and worth our time to read and understand. So the other kind of issue with informal models is that, they're basically trained to produce, highly convincing proofs, right? So they're always going to look good, even if they contain a mistake. And that is, really, really tricky to deal with, right? Without formalization, right? If there is, a proof, often as a mathematician, you get sent proofs by people which are wrong. And often there are kind of signals very early on that they have mistakes. And the issue with these big informal models is that they are really convincing and also still sometimes wrong. So yes, formalization, I think, is still going to be extremely useful no matter how good the informal models we get. So I hope that we'll sort of be able to interact with these systems in a kind of informal, naturalistic way with natural language, but with some sort of guarantee that there'll be a formal proof object underneath, right? I think that's the sort of future we want to go for. I have a few slides about kind of like different ways in the past that like computers have impacted mathematics that I'd like to kind of mention quickly. And because I think I want to understand, at least personally, like, what we should expect as these systems get more and more useful. So this is the EDSAC, which is at Cambridge. Well, probably not anymore, but was at Cambridge. So this was an early mainframe, right? And this was an early example of of a computer that really impacted mathematics, right? So Birch and Swinnerton Dyer did experiments on the EDSAC to do with counting points on elliptic curves over finite fields. And that led them to conjecture what's known as the Birch and Swinnerton Dyer conjecture, which is a conjecture about, I'll say conjecture about elliptic curves, right? But basically they did a bunch of computations and they saw something that they couldn't really explain, or at least that no one had seen before. And that led them to this conjecture. Now, the conjecture is one of the Millennium Prize problems, so it's one of the most important in mathematics, and it came from experiments on a computer. So this is a way that, past waves of kind of, automation made something possible that wouldn't have been possible by hand. And it's very interesting, but what was kind of, a bit different, I think, about this situation is that it was a mainframe, right? This was something that, only people, researchers who probably were only allowed to use it at night when, the weather forecasting people weren't using it or something like that, right? I don't know exactly the history with this machine, but that's sort of a common story. This is not sort of a widely accessible technology, right? It took a long time for computers to become small enough that, everybody could have one, right? And so, although this impacted mathematics, quite notably in this conjecture, it actually took a long time for sort of other mathematicians to be impacted by the availability of these tools. So something that happened, I think, a little bit faster was sort of like the internet, and archive, and tech, and things like that. So these were ways that sort of like mathematics was communicated and disseminated faster, right? And so this, I mean, I'm sure it still took a few years for kind of the internet, for example, to roll out. But things like the archive and tech, they basically, impacted all of mathematics relatively quickly, so to speak, right? Because they happen on the internet, and so people could kind of access them provided they had an internet connection, and it kind of sped up dissemination of new papers and this sort of thing compared to the old model quite rapidly, right? So there are faster feedback loops, more collaboration, like broader access to cutting-edge work. And I would kind of claim that the new kind of AI systems are close to the second thing, just because they're available, right? Like people can start using them, and okay, they probably do happen on a large computer somewhere, but sort of thanks to the internet, they are sort of accessible around the world. And so I feel like we're more in the latter camp, right? Where the deployment is going to be sort of much faster. The impact on mathematics is going to be sort of much quicker than sort of just readily available computation was. So I'm going to predict that AI will affect all areas of mathematics, maybe unlike computers did. And I want to think for a second about what's going to happen when computers can sort of routinely outplay us, so to speak, at proof search, right? And when chess in 1997, Deep Blue beat Garry Kasparov, some people predicted that chess was dead, basically. Some people predicted that sort of chess with human in the loop would actually still always be better, right, than sort of purely automated chess. That turned out not to be true. But yeah, the fact that chess would kind of die also turned out not to happen, right? Chess is actually probably more popular now than it almost ever has been. People stream it on Twitch, right? People enjoy, I think, the competitive element, right? People enjoy the intellectual stimulation. At least personally, I think that will still happen with mathematics, right? I think hearing an interesting proof will remain interesting no matter who produced it or what produced it. And so although I think chess is a reasonable analogy, there is a different analogy that I hope is actually a bit better, which is the Hubble Space Telescope, which is an instrument in space that sort of allows humans, astronomers in this case, to kind of see things that they never would have seen from Earth. So my kind of hope is that AI is going to let us see mathematical things that we would have been very unlikely to see otherwise, right? In this case, telescopes, space telescopes, etc., allow theoretical sort of physicists to kind of basically develop much of kind of modern physics, right? So these have been extremely influential in other areas of science, and so I hope that these sort of new instruments we have access to are going to kind of have the same impact on mathematics. So yeah, this is going to be my kind of like, I don't know, exaltation section where I would, ask you to take seriously the idea of working with an AI co-author in kind of lean and decide on some ambitious projects that you can tackle, right? So these tools are only going to get better, as I kind of mentioned. So I think it's worth your investment of time to learn how to kind of harness them effectively. I would also suggest that automated quality checks and things like that are going to be more important as more AI generated proofs from Aristotle, but also from all the other tools that are available start coming in. And people should experiment with kind of new workflows and interfaces, right? People got very used to kind of a way of doing things before that kind of worked when we were dealing with kind of managing human collaboration and humans signing up for sub-projects and kind of taking different parts of a large project and how we coordinate those. And I think the way we coordinate AIs will be quite different, right? Certain things that used to be problems, like accidentally giving two people the same task and having one of them be very sad their contribution didn't get merged, are no longer relevant, right? But certain other things that maybe, well, it will just be very different. That's what I'm kind of saying. So yeah, we should probably decide kind of as a community what kind of future performer mechanics we want when these tools kind of get better and better. So yeah, I'd love any questions that you have. Sorry that oh no, we're good, cool. And please try Aristotle and read the white paper. Thank you. Yes, we certainly do evaluate. I mean, autoformalization is, of course, like a super key part of everything you're doing, both to produce, problems to work on, but also for individual steps. And yeah, I guess there's a lot of different things you could do, and we have a sort of variety of signals to kind of try and get a sense of whether autoformalization is correct. Autoformalization is, unfortunately, not a formal problem, right? It's not formally specified. Saying whether or not something is a correct formalization sort of has, edge cases and places where humans would disagree. And that makes it, I think, quite challenging compared to the sort of formal correctness that you get. So yeah, we try and measure it, but I think it is definitely a harder task than with formal success rates, for example. Yes, we do, but I don't think I can talk too much about it. I'm sorry. Yeah.
So one question.
I'm going to express my ignorance in exactly what makes something rest. So there's I think so. I think the answer would be yes. And so when users use it, we give them a Python package, which makes it easy for people to use. But people who are, developers themselves, I think they can read the source of that Python package and the documentation, and they can probably work out how to query it themselves with whatever language they like. Yeah.
Cool. Yeah, there are a couple more questions. So one question by Ian Stark is, reinforcement means your system is less dependent on what human proofs are available. How much is it still shaped by what human tactics are available?
Oh, that's a great point, I think. Yeah. So yes. So yeah, with systems like Aristotle, they're using lean, and the sort of the tactics, they form like the vocabulary. And so that does change kind of quite extensively. Yeah, what sort of proofs they can express. Obviously anything that sort of has a proof in the system, that has a proof term, and in principle, Aristotle could just produce that proof term, but that proof term will, of course, be massively large in some cases, and that just won't really work after a point. So yes, you certainly do need a good set of tactics to kind of build on. That's what I was hinting at a bit with the first slide. I think a really interesting, future direction is, of course, AI writing tactics that it then uses itself, right? AI recognizing common patterns that it's having to repeat and kind of doing a sort of, I don't know if you'd call it meta learning, but compression of its own vocabulary by writing tactics. I mean, I think that would be super exciting.
There's another question by Martin Burger. Can you quantify how much compute you use for training, in particular reinforcement learning and day-to-day improvement?
No, I'm sorry. I cannot give quantities for training runs and stuff like that. Yeah, sorry.
There's another other two more questions. This one's a reinforcement method. So the person says, my understanding of DeepMind alpha proof is that the return is evaluated by a worst case from a given node, longest proofs in brackets, the longest proof in brackets in the tree search. Is that the same here? Is that to prevent the system making small incremental gains and leaving a lot to do later on? I can read it out.
Yeah, maybe just read the middle bit again. I'm
Yeah.
not quite sure. Or maybe I can read it.
Yeah. So my understanding of DeepMind alpha proof is that the return is evaluated by a worst case from a given node in the tree search. Is that the same here? Is that to prevent the system making small incremental gains and leaving a lot to do later on?
Yeah, I'm not really sure I understand the question off the top of my head, because I also don't really know exactly the alpha proof paper by heart. So yeah, I'm not sure. Sorry. Yeah.
And it's also fine to unmute master if you like. There's another question. Has there been any thought on understanding formal proofs created by Aristotle? That is, being able to understand or translate new formal proofs into human understandable natural language?
Yeah. So yeah, kind of deformalization. I think, yeah, a lot of people are interested in that. I think it's, there's the kind of the nuts and bolts of it, which is just you want to read a proof more easily, and it's more easy to read sometimes when it's kind of informal. I don't know if the question is getting at that. I think modern language models are quite good at doing that, especially if you kind of like augment them with some details about the proof state, etc. In terms of like, have we understood certain proof strategies? I think maybe, yes, there definitely are some interesting things, and maybe I won't go into the weeds right now, but I'm happy to kind of talk about, certain kind of quirks you notice from interacting with it. But yeah, I think language models are actually reasonably good at this now. So certainly a lot of people will take like, an output from Aristotle and ask, Gemini to summarize it and kind of have a kind of productive, interaction in that sense.
There's a new question that's popped up. So the notations, names, and tactics in main files are very different from informal text, so usual mathematics notation. The same notation in formal and informal text may be very different vectors. Do you have a special arrangement for them?
Arrangement with the embedding. I would just say, yeah, I mean, it's a regular language model in that sense.
Any more questions from the
Yeah, just one more question. Yeah. When you were talking about the rewards for reinforcement learning, are these kind of like one specific reward for its different problems, or are you like combining multiple rewards for its different?
Can you elaborate? Sorry.
Yeah, because you give like 4 bullet points.
Oh, yeah.
I was wondering if this is meant to be like different bullet points, like same some of them.
Yeah. So that was the bullet points were really contrasting different approaches that different probably people use a mix actually, right? But generally it's sort of different groups take different approaches. So certain models you'll find online or in papers have been trained with purely one of those approaches, right? Maybe it's informal reasoning for a correct numerical answer, and that's fairly common. Or maybe it's interacting with a Python REPL to produce the correct answer. Maybe it's the lean thing. So yeah, that was more like sort of big picture different reward signals you can use, and of course, yeah, some people will use combinations.
Yeah.
So thanks so much.
Yeah. Mm-hmm. So we start with a pre-trained model, which has already seen much of the internet. So in that sense, a lot of stuff is in there already. And then we do our stuff. So in that sense, it's hard to say exactly what it hasn't seen, but probably a safe assumption is that it's seen everything once, you know what I mean? Like these pre-trained models are pre-trained on extremely large data sets collected, on all over the internet, big scrapes of blog posts and articles and code from GitHub and all this stuff. So the pre-trained models, I think they also maybe don't say exactly what the mix is, or maybe they do. It depends on which model you start with. But yeah, I think a good approximation is that you are starting from a base that has seen a lot of text, right? The majority of the text you could think of that's available on the internet probably has been in the pre-trained.
Okay, so
Right. Yeah, exactly. Yeah. 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 So that's sort of yes, exactly. Right. So yeah, with the pre-trained model, it's kind of seen everything. So it's seen good stuff, it's seen bad stuff, but it's kind of learned how to represent everything. And the RL process is sort of sharpening the distribution towards, producing correct, in our case, mixed informal formal proofs. But yeah, I think that's like a good way of thinking of it. It's the base model kind of knows how to do everything, but doesn't quite know what it's trying to do. And then the RL teaches what it's trying to do. Yeah. Yeah, of course. Yeah. I think with these things generally, it's sort of the more data, the better. I think that's sort of a pretty good principle to live by. Hmm. Yeah. I think, there's a few different approaches. I think from what I've seen of alpha proof, I've not, used the latest version, for example, or used any version, but at least the initial version, the version that they wrote the paper about was a purely formal model. And, it was, it sort of extremely sort of specialized and slightly used slightly kind of strange syntax and kind of these things. And it wasn't particularly human aligned or kind of informal math aligned. So I think they took the approach of kind of really just like formal maths and solving the proof is that the only, thing that matters. And, the model kind of reflects that. With regards to other systems in the IMO, I think another difference is maybe, I think a lot of systems were kind of starting from kind of more general informal reasoning models and kind of putting sort of lean in on top of that, or sort of formalization on top of that, sort of as a second stage or as like an afterthought, which is a bit different to our approach, which is kind of like sort of lean from the ground, or kind of, lean all the way, if that makes sense, or at least mixed informal. So I think they definitely have very different qualities when you look at the proofs. Like, I don't know, I could definitely tell them apart, put it that way. And you kind of see, some things about how they prove things, or the verbosity of the proofs that, or the way that they, break things down, that are kind of indicative of, how they were trained, for example. So yeah, there's a few different approaches for sure. And yeah, surprisingly, I mean, I think a few of them got very similar results. And of course, there was the informal only reasoning models, which got very similar results. So Yeah, you probably want to run it yourself, but yeah, it is checked as it goes. So all the things that you submit to us run on our machine rather than on your machine, if that makes sense. Does that answer the question?
So then your output is checked by me.
Yeah. Yeah.
I suppose check.
Yeah, exactly. It will have compiled on our machine, and you should probably do it anyway to check, there can be minor mismatches in like the version or the packages you're using, or I don't know, some bug on our end, for example, but hopefully not, but yeah, it has happened. But yeah, in principle, anything we give you back has been checked by Lean already. Yep. I don't think I can publicly commit to any plans. So, no. Yeah, I guess my personal opinion is that there is a lot of overlap between, what's needed inside one of these models to produce formal proofs, right? And a lot of the tactics in some languages are inspired by a similar one in another language. And yeah, a lot of it is just kind of a problem of translation. So I wouldn't be too surprised if you could take a model that was, for example, very good at Lean and put in a lot less effort than you would have to do to train it from scratch to produce a model that was good at Isabelle, for example. I think there's a lot of kind of, shared representations internally in these models that would mean that you got a lot of benefit from starting with a model that was already expert in one language. Yeah, exactly. So actually, it's a good point. So people do that. People have submitted queries to Aristotle where they just input a file that's written in Coq, and they say rock and say translate this to Lean for me, and it does a reasonable job. And that's sort of like an emergent property, you could say, just because of the way these things are trained, that they kind of share the representation internally, and so they're actually quite good at doing that sort of thing.